Ok. Allora un piacere avere Alexander Bufetov da Marsiglia, CNRS, che ci parlerà di sine-process as excess one.
Ma inglese o italiano facciamo?
È inglese.
Inglese? Sì, va bene.
Chalk is
okay. Allora, okay. So let us start with some notation, and just I will consider in this talk I will consider the sine process. So the main object for me is the sine kernel, which is the kernel of orthogonal projection on the Polynomial space. So I consider this as kernel of orthogonal projection of L2R to Polynomial, to the classical Polynomial space. Okay, and to this kernel there corresponds probability measure. So probability measure, so-called sine process, is probability measure on space of configurations on R. Space of configurations on R. So what do I mean by space of configurations? These are just points of the these are just, excuse me, subsets of the real line without accumulation points. No accumulation points.
Sasha, there is a...
Yes?
One can see until conf R.
Yeah, you are outside.
Okay, because there was no mark. Okay, just 1 second. Okay, I will mark the limit. Yes, okay, so like this is okay. Well, not really. Just 1 moment. X, where X is subset of R, that has no accumulation points. Has no accumulation points. Is this okay now?
Yes.
Okay, good. So, and okay, so sine process is measured on such subsets. And for me, most convenient way to define such measure will be to define it through multiplicative functionals. So on such space, I have multiplicative functionals. So just product of value of the function over particles of the space. Over particles of the space. And so to define such measure, it is necessary and sufficient to define expectations of all such multiplicative functionals. And so expectation of such multiplicative functional is given by Fredholm determinant of this type. G minus 1 S. So this is this formula can be understood in the following way. So it is often more convenient to write determinant in symmetrized form like this. One can assume for the beginning that G minus 1 has compact support, at which point this operator has finite trace, because S obviously has finite trace locally. So this operator has finite trace. And this one, it is possible to consider not just Fredholm determinant, but in fact Hilbert-Karlman regularized determinant. Hilbert-Karlman regularized determinant, and then it comes down to the same thing. And then it comes down to the same thing. Okay, so this much is definition of sine process. Sine process arises in many different problems, but specifically in the study of eigenvalues of random matrices. So it describes, it was introduced by Freeman Dyson. So Freeman Dyson in the study of eigenvalues. And so the question that I addressed in this talk, is the question of relation between random sets of this sine process. So these particles in the sine process may informally be considered as eigenvalues, as I say, limiting eigenvalues of an infinite matrix. In fact, this can be given precise sense. Let me pursue a little digression for this. So, one of ways of precisely seeing the sine process, a little bit different from original construction of Dyson, is through so-called Quaker measures. Quaker measures. So one can consider a measure, one can consider the Haar measure on the unitary group. So we consider a unitary group endowed with Haar measure. Then we can make Cayley transform. And instead of the unitary group, we have the space of Hermitian matrices. So the Cayley transform takes the unit circle to the line, and so the purely the eigenvalues of absolute value 1 of the unitary group it takes to the real eigenvalue of the space of Hermitian matrices. And this space of Hermitian matrices is at this point endowed with the measure d mu n. So the measure d mu n can be written explicitly. Let me write it explicitly. So d mu n is the following measure: determinant of 1 plus h squared to the power minus n dh. This is the measure d mu n in these coordinates. And then it is clear from the definition that these measures have the projection property. So if I consider now the space un plus 1 with Haar measure, so now it goes to the space, again the Cayley transform, it goes to the space hn plus 1, dun plus 1. So, and there is a natural map from hn plus 1 to hn, namely the map of cutting a corner. So one considers a matrix n plus 1 times n plus 1, and then one cuts one column and one row. So under this operation, the measure mu n plus 1 goes to the measure mu n. And this, in fact, is clear if one keeps in mind the construction with unitary groups, because, of course, Haar measure is a unique unitarily invariant measure on the group un. And, in fact, the image of this measure, so there does not exist a homomorphism from un plus 1 to un, it is not possible. But there does exist a map which is equivariant under the action of un, under the action here. So, and this is precisely this map of cutting the corner, this is the map. So obtain a measure, so these measures form a projective family, and we obtain a measure on the space of infinite Hermitian matrices. Infinite Hermitian matrices, which is projective limit of finite Hermitian matrices. And so the measure is naturally, the Polynomial measures are naturally lifted to this projective limit. And by the way, let me point out that they're called Polynomial measures because they were first considered and studied by Quaker. Okay, so, and then also by Pickrell. So yes, so these infinite Hermitian matrix, this infinite Hermitian matrix is not an operator. It is not, it doesn't act anyway. It's just an infinite Hermitian matrix. A projective limit of finite Hermitian matrices. It is not an operator. It has an action of the infinite unitary group, of the inductive limit of these groups, and it has also asymptotic eigenvalues, which are not eigenvalues of any operator, but in fact they are asymptotic eigenvalues in the sense that the eigenvalues of these matrices, suitably renormalized, converge to an infinite collection of values which are asymptotic eigenvalues. So if eigenvalues of these matrices we denote lambda k n, then lambda k n over n converge to some limit which I denote xk. And this configuration of xk's carries a measure, and this measure is precisely the sine process. So sine process arises in this way in decomposing Haar measure, So in decomposing, in considering the image of Haar measure on eigenvalues. So there is no group, but there is an infinite dimensional homogeneous space, the space of infinite dimensional Hermitian matrices, so the space H of which is the projective limit of Hn. There are measures on each individual Hn, which are just measures of eigenvalues. So here they're purely imaginary, here they're real. And there is limit of measure on eigenvalues, scale. There is limit on scale of measure of eigenvalues, and this is precisely the sine process. This is one of the ways of seeing the sine process, different from the way of Dyson, in fact. Okay, so let me now say sine process also appears in many other situations. Let me now say that the main point of my talk will be the relation between the sine process and the Paley-Wiener space. The Paley-Wiener space. So the Paley-Wiener space and the sine process. This is the main point. And so let me formulate a theorem of Gauche. A theorem of Gauche. So on the sine process. So a theorem of Gauche says that if I consider almost every configuration of the sine process for almost every, this is my measure, sine process, almost every configuration x, duration x, the family of reproducing kernels corresponding to this configuration, the family of reproducing kernels, so S, X, where X is an X in my configuration, spans the whole Paley-Wiener space. Paley-Wiener space. So, in other words, this set is a set of uniqueness for the Paley-Wiener space. there does not exist this random set, this random configuration, is uniqueness set for Pelley-Wiener space. That is to say, there does not exist a Pelley-Wiener function which is zero at all these points. And I should say that in joint work with Xu and Shamov, which will hopefully soon appear in GEMS, we proved such result for any, so this is, gosh, is 2011, and this is 2020 and plus, and going, which will, we proved such result for any determinantal point process, for any point process for which expectations of possibility functions are given by determinants, we have such result. We have such result. Okay, so the question that I would like to address in this talk is the question of minimality, of this configuration. So let me point out, let me be clear that this configuration, so let us reformulate this result equivalently. The family EITX, X is in configuration, so this is X, and T is the variable, is dense in L2 of minus 5 pi. Is dense in L2 minus 5 pi. So let me make it very clear that there is no chance that this family be Arie's basis. So not Arie's basis. Arie's basis for a very simple reason. For a very simple reason that there exist particles which are very close to each other. So just as with eigenvalues, while probability of matrix with multiple eigenvalues is 0, at the same time probability of matrix with small eigenvalues, very close eigenvalues remains positive. And in fact, here it is, since we're considering an infinite configuration, there always will be eigenvalues arbitrarily close. So this subset is not separated, and so it will not be Arie's spaces. It is not possible that it be Arie's spaces. It is nonetheless a uniqueness set, and the question is whether it is a minimal set. So let us look at the finite dimensional analog of this problem, so precisely on the group UN. So the measure that we are considering on the group UN, so the measure on eigenvalues of a unitary matrix, the measure of eigenvalues of intervalues, so UN UN goes to UN to, well, the Cartan subgroup, Tn, so the matrix U goes to spectrum of U, which is obviously on the unit circle, so it's all on the torus. And the measure, the Haar measure, goes to the following measure, the circular unitary ensemble. So K less than L, product d theta K over 2. So this is just the circular unitary ensemble. So please observe that this term, the square of the van der Monde determinant, precisely is responsible for the repulsion of eigenvalues. So the eigenvalues repel each other because of this term. So the kernel of this space will be, K. The kernel of theta 2, let me write it in additive notation, will be sine n theta 1 minus theta 2 over sine theta 1 theta minus theta 2, and there is a 2 pi. Here there is a 2 pi, and here it's in fact over 2. So this will be the reproducing kernel in this case. And the analog of the Paley-Wiener space in this situation will be the space of trigonometric polynomials of degree up to n. Of trigonometric polynomials of degree n minus 1. Of degree n minus 1. Now, I have n particles and polynomials of degree n minus 1. So it is clear that the polynomial of degree n minus 1 is uniquely determined by its values at n points. So a realization of this measure is of course a uniqueness set, but it is also a minimal set. Because indeed, on the one hand, a set of n points is uniqueness set. So a polynomial of degree n minus 1 cannot possibly have n roots. If it has n roots, it is the zero polynomial. And at the same time, for any n minus 1 values, it is possible to give a polynomial which assumes these values. So it's uniqueness and minimal. So this configuration is uniqueness set and minimal set. Uniqueness set and minimal set. This is precisely what is not the case in infinite dimension. And so now I'm ready to formulate the main result of the talk. So the main result of the talk is that the family, so this is on the archive since 2019. The archive 2019. So that for almost every configuration, okay, so the set X, almost every configuration X, and the particle, any two particles P and Q in X. So the set without one particle is still a uniqueness set. A uniqueness set. Whereas the set without two particles is not anymore. Is a zero set from the Paley-Wiener space. Zero set from the Paley-Wiener space. For Paley. And equivalently, the family e to the itx, x in x without p, so without one exponential, is still dense, but without two exponentials, not anymore. So without two exponentials, not anymore. Not dense. And this is the main result of the talk. This is the main result of the talk. Okay, so maybe any questions about the formulation of the main result? Because if the formulation is not clear, then the remainder cannot be clear either. Questions? Not any questions? Okay, so I continue. I continue. Okay, so first of all, well, to show that it is a zero set, one needs to exhibit a function which is zero at this set, and this I can do quite explicitly. So the function I noted, so let me consider the function gx of t, which is the product in principal value. So over all x in x of 1 minus t over x. So this is the function. This is analog, so if I write it like this is analog of characteristic polynomial of a matrix. This is analog of characteristic polynomial of a matrix. In fact, it is not possible to go to the limit of characteristic polynomial when size of matrix goes to infinity. The product will diverge. It is nonetheless possible to consider a ratio of these two characteristic polynomials. It would be easier if I write, so let me point out that product like this, t1 minus x, t2 minus x, over x and x in principal value is nothing but gx of t1 over gx over t2. There we go. Okay, so now this function is not in perimeter space. Nonetheless, if I remove two particles, so I consider the function gx of t over t minus p t over t minus q, then this function is in perimeter space. This is my result. Whereas, in fact, the first part, this requires effort to prove it, it's not immediately clear, but the first part, in fact, is equivalent to saying that g of x over t minus p, that if I divide by only 1, then this is not in perimeter space for the simple reason that it is not in L2. Observe, by the way, let me make a remark, that if it were in L2, it would automatically have been in perimeter space, because perimeter space has such property that if, so let me make a remark, that perimeter space has the property that if f is in perimeter space and tf is in L2, then this means that tf is in perimeter space. So this is clear, immediately clear by taking the Fourier transform. And so, in fact, if this function did belong in L2, it would have automatically belonged to the perimeter space because of this. But in fact, it is not, and this is the whole point. So this statement I can prove in a certain form of generality, in some generality, whereas this statement is specific to the sine process. And in fact, let me start. Here I have finished with formulation of the result. And again, let me ask if there are some questions. And if there are no questions, I will pass to an outline of the proofs. So if there are any questions about formulation of result.
I don't see questions.
Okay, so then I pass to discussion of proofs. So, and let me first explain this part, which is both simpler and more general. So let me start with outline. So outline of the argument of this. So let us say that this is 1, this is 2. Outline of proof for 1, and it is quite general. So you will see that it's quite general. So what the outline of the proof of 1 uses is the representation of this function gx of t as Radon-Nikodym derivative between palm measures of the sine process. So palm measure of the sine process is conditional measure subject to the condition of having particle in given position. So I say palm measure is conditional measure subject to a particle at P. So subject to the condition with respect to a particle in P. Okay, and then it is a key consideration that Radon-Nikodym derivative between palm measures at 2 points at configuration X is nothing but Gx of P over Gx of Q squared.
How do you spell palm? Just to have a...
Palm is like this, palm. Conrad palm. So palm, he was, in fact, as I said many times, Palm was not a mathematician, actually. Palm was engineer. He was working for Ericsson in Stockholm, and I don't think he knew what measure is, in fact. So, and at least he didn't write in these terms. He wrote in his main work, he wrote in engineering journal, and in fact, it was Hinchin, Russian mathematician, who constructed the mathematical theory of palm measures. And in fact, in Russian literature, you find terminology palm-Hinchin theory. Okay, so the ratio of palm measures is in fact given by this formula. So specifically, yes. So specifically, we can normalize by some gx. We take q equals 0, normalize. The main point for me is how this depends on p. So now the key point is that obviously the expectation. So let me explain this point in detail. It is not difficult, but absolutely essential. So the expectation of obviously the Radon-Nikodym derivative. So we fix q for A, fix q, and for A, the expectation with respect of the palm measure with respect to the measure q is of course equal to 1 because it is Radon-Nikodym derivative, in fact. It is Radon-Nikodym derivative. Therefore, the expectation of the square of the function divided by, so let me continue. So I erase this part, the part 2, because I stay with part 1. So I need to prove part 1, but in fact this space should be enough for me. So the expectation of gx p squared dp over p minus x naught square, where x naught is some other particle, and integral in R such expectation is then finite. Because the expectation of this one is 1, so Q is fixed. This expectation with respect to PQ. This expectation is finite. So here Q is fixed, P is variable, and this quantity is precisely the L2 null of this quantity. Here there is division by Q. So, unfortunately, my notation is not very wisely chosen. Excuse me, I changed it. I do something that one should never do, namely change notation in the middle of a talk. But this is the advantage of having the blank. So I will use it. Okay, excuse me. So I want to say gx of t dt, and this x naught I denote p. T minus P. Now this is fine. So P particle, P in X. Okay, so now the two notations are consistent. Okay, so I have a Q here. So the configuration X does not have Q, so it corresponds to Gx of T over T minus Q. Because of this Q, because of Pound measure, because of this particle. I divide by P, but in fact I divide by P. So square. So this is precisely saying that the L2 norm of this quantity is finite. End of story. One only needs to show, so I have shown that this belongs in L2. This belongs in L2. I also need to show that it not only belongs in L2, but that it also belongs in Peli-Wiener space. But this in fact follows from this representation of Radon-Nikodym derivative. This Radon-Nikodym derivative, considered as function of T, must in fact belong in the space. So if it is integrable, it must belong in the space for, shall we say, general reasons of linearity. I would like to underline here that this argument is not specific to the sine process. This argument is not specific to the sine process. This argument works in significantly greater generality for Airy, Bessel, and many other processes of random matrix. Okay. So let me now give the outline of the more difficult step, the outline of the proof of 2. So now I need to give an outline of proving 2. So the fact that Gx T over T minus P is not in L2. Is not in L2. Okay. Is not L2. Is not in L2. Okay. So why is it not in L2? Here we need to consider the logarithm of Gx of T. So Gx of T is multiplicative functional, so its logarithm will be additive functional. We only need, by the way, in these considerations, in considerations of characteristic polynomial, there are two considerations. It is important to consider the real part, and it's important to consider the imaginary part. So in this notation, the modulus and the argument for complex vectors of T, that is. But for me, it is only important to consider the modulus. It's only important to consider the modulus. So this is sum log, clearly x, sum over x, log x minus t minus log x. So for normalization. So it will be convenient for me to consider not this sum, but regularized sum. So regularize and consider the sum, regularize, and consider the sum where I put plus I epsilon here and plus I epsilon here. It will be very clear why I want to do this, because in fact, this puts my function, this function, in the Sobolev H1 space. In the Sobolev H1 space, which, let us recall, is the space of functions such that the integral f of x minus f of y over x minus y squared dx dy is finite. So this is my space, FNL2. So space of functions with half a derivative. The integral that is written here is nothing but, of course, the inner product of the function and the Hilbert transform of the derivative. So it is in fact 1/2 the derivative. So this regularized function is what I would consider. And the main point is that this function satisfies the central limit theorem. Satisfies the central limit theorem. Has variance log t. There is some constant depending on epsilon, but let's not think about it right now. So, and therefore, and moreover, these functions, which let me denote as t of x, for different values of t, there is some independence. Values of t, some independence. This is a tricky technical point, which I don't want to explain in detail because we don't have time, and it requires a certain setup. In fact, they are not, let me say just very briefly, they are not independent. To ensure independence, one needs to do a frequency decomposition. So frequency decompositions for different values of, so one needs to decompose in the frequency space. So consider Fourier multipliers on intervals of logarithmic scale, and they become independent for different values of t. The important frequencies in this problem are the low frequencies, and the bigger the difference between 2t, the lower are the frequencies which become independent. As I say, please allow me to refer to the preprint for precise formulations. They're a little bit heavy, and let me not write it here. The point is that there is some independence, and therefore, the event that this function, let me put square. Well, square or not square doesn't matter. The event that this function has value about 1. So the probability of such an event, because of the central limit theorem, is roughly 1 over square root of t. And because of the independence, in fact, one can use the inverse of the Borel-Cantelli lemma. In fact, what we use is the Pelly-Zygmunt inequality. It's the Pelly-Zygmunt inequality. So one can say that these events are sufficiently independent so that once this series diverges, there happen infinitely many of them. And this is precisely what concludes the argument. So, because since this function infinitely often takes value at a constant, again, one needs to be a little bit careful to ensure that the integral diverges, but one needs to do another averaging, but this can be done without any difficulty. In short, here again, I'm skipping some technical details, but precise formulations are in the preprint, but the idea is that this event, where this function has value 1, value constant, has probability 1 over square root of t, this series diverges, and therefore this event takes place in the and therefore this function does not belong in L2. And in the remaining couple minutes, let me just say that the main point in proving this central limit theorem. So this central limit theorem is proved using second theorem of Ségur, but here I just need not only strong Ségur theorem, but in fact strong Ségur theorem with a return. So this theorem exists. It's called Borodina-Okounkov-Geronimo case formula. called Geronimo case formula. And in fact, what I need is scaling limit of Borodino-Penkov and Geronimo case formula, and its scaling limit. And in fact, what I prove, the proof consists in two steps, in one of which I, in fact, take a scaling limit, whereas in the other, I use the proof that goes back to Vidal of this formula. So there are many proofs exist of the single-second theorem and of the single-second theorem with error terms of Borodino-Penkov Geronimo case formula. So one should say that the paper of Geronimo case is 1979, the year I was born, whereas Borodino-Penkov paper is 2000, the year when I finished university. But in fact, it is after Borodino-Penkov proved the result that people saw that, in fact, Geronimo case had this paper with this result a long time ago, and just it was not noticed in the community. Okay, so let me just very briefly formulate the result. So I take function g, which is exponential of phi plus phi minus, where phi plus belongs to Dirichlet space and phi minus belongs to the conjugate of the Dirichlet space. I consider the multiplicative functional corresponding to this function g, so the corresponding Repulsion determinant. And then I write the formula, which is quite similar to, obviously, the theorem of Segur. So I have phi hat of 0, phi is the sum, phi hat of 0, then the term, precisely the inner product of phi plus and phi minus with inverted frequencies in 1/2 Sobolev space. So this is the term of the central limit theorem, in fact. So this is what ensures the central limit theorem. And then there is another term. There is a Repulsion determinant of Hankel operators corresponding to function, so generalized Hankel operators, corresponding to the function h, where h is, let me write it somewhere. Okay, let me erase the definition of h on half space. So, though I use it all the time. So, okay, so h is exponential of phi minus phi plus, and the Hankel operator is the same thing as in the discrete case. And there we go. And the fact that these functions are in the Dirichlet space ensures that this Hankel operator is Hilbert-Schmidt operator, and therefore this combination is operator finite trace, and this is precisely the error term in the Segur formula, and this is precisely what one needs for proving central limit theorem. Let me put a little bit quotation marks in the central limit theorem, because it is almost central limit theorem. Maybe it is better to say that there are estimates both from above and from below. This is essential for independence, that there are also estimates from below for Gaussian tails of this random variable, precisely from here, because this determinant one can estimate both above and below. And from here, it is possible to prove, as I said, analog of central limit theorem from this variable, and from here, it is possible to prove this statement about, in fact, large deviations for this random variable. So what is important for us is not when this normal random variable is of size square root of variance. But what is important for me here is not situations when it has size square root of variance, but situations when it has size variance. So variance is logarithm, and I really want to know when it is indeed logarithm, because in fact here I want to know when this has size t, so which means precise exponential of variance. So this should have size log t, so size of variance, not square root of variance, but variance. So precisely using this analog central limit theorem, we obtain such estimate. And using independence in applying this result, this open German case formula at different times, we obtain the main result. There is an important technical difficulty which I'm completely hiding under the carpet. That is estimating high frequencies of the characteristic function. So estimating characteristic function of this quantity for big values of lambda, where this formula is not enough and one needs more work. But let me just say that using and developing of this formula, one is able to prove the main result, that this function does not belong to L2, and therefore realization of sine process without one particles is still uniqueness set for the Polynomial space. Thank you very much.
Okay, thank you, Sasha, for the very interesting talk. Are there questions, remarks? I have a question. Which is something. No, the fact that you have the Dirichlet norm playing a role.
Yes, because it's here.
Right.
It's the variance. It's the variance.
Variance, yeah.
It's the variance, yes, of course.
And that is a conforming variant. Does it?
Yes, you mentioned this,
Yeah.
but I don't see.
Something,
I don't see how. I want to see this, but I don't. I would like to see this play a role, but I don't. I think this should. You mentioned this question. I think this should play a role, but I don't see how.
for further discussion.
Maybe we should discuss this more. Yes, exactly. Maybe we should discuss this more.
Are there other questions? Osservazioni? Okay, well, it's a second session. Thank you very much.